we are going to look at our final unit, Unit 3, which covers chapters 6, 7, and 8. This was our unit circle, trigonometric, polar unit. So at the top, we're going to kind of do a rough sketch for our 3 trigonometric functions. First one, y equals sine of x, could also be sine of theta. Start at my origin. At pi over 2, I'm at 1. Pi, I'm on the x-axis. And this would be 1 period. And then it does continue on forever unless if there are domain restrictions. So that is my function for sine. Next, we're looking at cosine. Cosine starts at positive 1. So it is a shifted version of sine. So that is 1 period, but we know it looks like that. For tangent, I want to grab a different color. Tangent is by definition sine divided by cosine. So wherever cosine is 0, so on my x-axis, I have vertical asymptotes because we cannot divide by 0. So I'm going to draw these in. And we could calculate tangent by hand, but our graph will look something like this. And we know it kind of goes off there. So there's tangent. Sine, cosine, and tangent, they come from our unit circle. So next we're going to look at some trigonometric functions. On the Google Doc version, this is in color. So you can see like the original, and it's getting shifted over. The amplitude we can measure from the midline up, and we can see the vertical shift here. And we're going to do that to both the graph and the equation. This equation is represented in this graph, but I want to address how we can find these characteristics in both. So I'm going to grab some extra colors here. I am going to start by measuring the length of the period, and I can measure period from like peak to peak. So maximum to maximum, I can do minimum to minimum. I can find like a middle point as long as it's one cycle before it starts to repeat. So this would be pi over 3 to pi. So from the graph, the length of my period, I would subtract pi minus pi over 3, which gives me 2 pi over 3. If I look at the equation to calculate period from an equation, I am going to look at the length of the period divided by b, where b is the number in front of x. So for sine and cosine, I'm doing 2 pi divided by b. If I'm looking at tangent, it would be pi divided by b. But I'm using 2 pi because I have a cosine curve. So 2 pi over 3, since that's my b value, I have the same length of the period, which we found in the graph. My midline is directly in between the max and the min. So for this graph, the midline is at 1. And from the midline, we can measure our amplitude. So we could do midline to max or midline to min. So this is our midline, and this is our amplitude. Here we can see that positive 1 is that vertical shift up. That also represents our midline. So let's go ahead and label that. And then our amplitude from the graph, we can measure it. Well, it starts at 1 and goes up to 3, so that would be an amplitude of 2. Looking at our equation, our amplitude is our leading coefficient, the absolute value of it, because the negative means something else. So a negative in front means that we do have a reflection over the x-axis. So I'll make a note of that here. Sorry, my hand's in the way. And then underneath, we're going to look at some other trigonometric graphs. So here we are looking at the reciprocal identities. So we have cosecant. Cosecant is the reciprocal of sine. It's 1 over sine. So I'm going to take a pencil and I'm going to sketch in my sine curve, which looks like this. That would go back up. Oh gosh. Because if I know that this by definition is 1 over sine of x, I can calculate at each of these. When the value of sine of x is 0, I'm going to have vertical asymptotes. So I have vertical asymptotes there. And the graph of cosecant are these u's that meet at the maximum of sine and the minimum of sine. So the graph of cosecant are just these u's, not the pencil part. That was just a reference for cosine, or for sine, I'm sorry. Next one we're looking at is y equals secant of x, which is by definition 1 over cosine. So I'm going to sketch in cosine in pencil so I can see where those max and mins are. And know where my asymptotes are. So my asymptotes are where my cosine values are 0. And so the graph of secant looks something like this. The last one is cotangent. Cotangent is 1 over tangent, or cosine over sine. For this one, we have asymptotes at 0, at pi, 2 pi, 3 pi, basically k pi. And for cotangent, it looks like a reflection of tangent. So it goes the opposite way. So as we read cotangent from left to right, it's decreasing. But if we look back up here at tangent, as we read from left to right, we are increasing. But we could create this shape by reflecting it. So back down here, and I'm just going to add in that one. Underneath, we're looking at inverse trig. This is arc sine. It could also be written out, so we do want to be able to recognize both. Same thing here, arc cosine and arc tangent of x or of theta or whatever variable we are working with. For arc sine, if we are asked to evaluate a value, we are looking at the right side of our unit circle because our range is from negative pi over 2 to pi over 2. And that's because if we were to sketch a graph of sine, sine looks something like this, and I'm going to continue it this way. We're looking at this rectangle right here for the inverse to be a function, for it to be invertible just on this domain, and this is from negative pi over 2 to pi over 2. For arc cosine, I'm actually going to start with the trig graph. So arc cosine looks, or our cosine curve looks something like this. And so if we want a piece that's invertible, so the inverse is also a function, I want to look at this window. And this is from 0 to pi. So when I look at my unit circle, 0 is on the right side of my graph. Going to pi, I'm going the top of my unit circle. So our range is from 0 to pi. For arc tangent, we're going to look at our normal tangent graph, which looks something like this. And I'm going to try to line this up. Something like that. I want this middle one. We always want to center it around 0. That's why we pick these ranges. And so this is from negative pi over 2 to pi over 2. But knowing the graph of tangent, there are asymptotes right here. So it's not going to match the range of arc sine. We cannot include those asymptotes, so we're having parentheses. So not including negative pi over 2 or pi over 2. So looking at our unit circle, we don't include those values, but we still want the right side of our unit circle. All right, we're going to move on to the next page. There are only 2 pages of notes here. So next we're looking at transformations for our trigonometric functions. So we have sine or cosine. We could also have tangent, and I'll talk about that when we're filling these out. So this is the template for a trig function. When we look at our a value, yes, that does represent a vertical dilation, but in this aspect, we want to think of it as our amplitude. The measure from our midline to our maximum, or our midline to our minimum. So this would be our amplitude, that height right there. I want to make a little note. If A is negative, we cannot have negative amplitude. What that means is we have a reflection over our x-axis. So our amplitude is the absolute value of it, and if it is negative, it just means that it was flipped. Our b value has to be factored out of parentheses because that will affect our phase shift, but this helps us calculate our new period, or how our period changed. So when we're looking at sine or cosine, we want to calculate our period by doing 2 pi over b, whatever that value is. But since tangent has a different length of its traditional period in its parent form, we only want to do pi over b. For our phase shift, we kind of always worded it as it's the opposite of what we think. So if it's plus something, it's actually going to the left, and if it's minus something, it's actually going to the right. That last number at the end, our d value, is our vertical translation, how far it's going up or down, but that also is our midline. So if a question asks us for a midline and we know what this value is, it's very easy to see. So we're going to look at some other trig and other identities. These are mainly formulas that I'm going to talk about that we do need to be able to use and have ready at the forefront of our brain for those tricky rewording or simplifying trig equations or expressions. So in the first one, we have sine. We could write it as 1 over cosecant. And then cosecant is 1 over sine. For cosine, we can rewrite that as 1 over secant. I would never make it more complicated, but it is good to know. And then secant is 1 over cosine. Tangent of x or of theta is sine of x over cosine of x. Cotangent we can think of as 1 over tangent, or in terms of sine or cosine, we can take this fraction and do the reciprocal and get cosine of x over sine of x. Next, we're moving on to our Pythagorean identities. We have sine squared plus cosine squared equals 1. It comes from our Pythagorean theorem, x squared plus y squared, or a squared plus b squared equals c squared. Here, similar thing. We can get our other two versions from manipulating this one. So if I divide everything by sine squared, I would get 1 plus cotangent squared equals cosecant squared. And then if I divided everything here by cosine squared, I would have tangent squared plus 1 equals secant squared. For our sum and difference identity, we have cosine of, I'm going to use a plus b, and that is equal to cosine of both, so cosine of a times cosine of b, but then we have the opposite operation to what was here. So if there's a plus originally in the parentheses, it's a minus here and vice versa. And then I have sine of both, so sine of a times sine of b. If I'm calculating sine of a plus or minus b, then I have sine of a times cosine of b, same operation, cosine of a times sine of b. It helps to remember that if the signs are opposite, the pairs have to match, and if the pairs are opposite, the signs have to match, and then you have to associate that with either sine or cosine, the correct one. Our double angle identities, we have sine of 2 theta equals 2 times sine of theta times cosine of theta. And then for the double angle identity for cosine, we have 3 versions. So cosine of 2 theta could be cosine squared minus sine squared. It could also be equal to 1 minus 2 times sine squared, or 2 times cosine squared minus 1. Ooh. All right, and then our last section, which was our last chapter, chapter 8, we have polar graphs. So these were the equations for circles. If I have cosine, that means my circle is centered like on my x-axis. So if my a value was positive, it would go on the right side where the diameter reaches that a number. And then if my a value was negative, it would just go on the left side where it still reaches that value for a. Remember, because in polar graphs, we have r comma theta, and if we have a negative r value, or we plug in a value and it turns it negative because the a is negative, it'll push it to the opposite side. So for sine, if I have a positive a, it's going to be centered on my y-axis and still go out to a. If my a is negative, it'll be centered on the y-axis for the sine version and be on the bottom. We're moving on to roses over here. If we have cosine, we will have a petal on our polar axis, or we can think of that as our x-axis, because there is cosine in our equation. Let me go back to this real quick, I'm so sorry. If our a value is negative or positive, the petal will be on the positive side, so the right side, and if it's negative, it flips to the other side. But either way, it'll be on the polar axis for cosine. For sine, it will not be on the polar axis. There will not be a petal on the polar axis. And then under here, I just want to make a note. If n is odd, then we have n number of petals. So if it's 5, we have 5 petals. If n is even, we have double that. So we have 2 times n petals. So if n is 4, we have 8 petals. Lastly, we're looking at limosons. We have our cosine template, our sine template, and we're looking at what these mean. So if the absolute value of a is less than the absolute value of b, that means there is a loop. So in my graph, it kind of would go around and like loop in the middle. For this, the value that it reaches out here, and for all of them, is the absolute value of A plus the absolute value of B, whatever those two numbers are added together. The distance it reaches in the inner loop, so this one there, we're looking at the absolute value of A minus the absolute value of B. If the absolute value of A is greater than the absolute value of B, we're going to have a dent. So it'll look kind of like a kidney bean. I'm going to do my best to sketch a picture here. But it'll look something like that. Oh gosh. And then the distance it reaches on this outer edge is still A plus B. And then where the dent reaches on the inside is A minus B. Both of these are cosine versions because they're centered on the like x-axis or opening on the x-axis. And then the last one, if they are equal to each other, we have a point at the pole, so at the origin. We'll do a sine one this time. And it'll kind of look like a heart. The distance it opens out here is still the absolute value of A plus the absolute value of B. And then these are the A values or B values because they are the same. And that is your quick recap from Unit 3.